let me record it. Yeah. Yeah, so it's our pleasure to have Roger to give this wonderful talk. I think this should be a very important protocol for especially for Solana and for sure for the whole blockchain community. The latency will be much lower. So it's very nice to have Roger here for the talk. And this event is organized by Decentralized AI linking group and also by Toronto Samir. Yeah, Samir is here. So yeah, Roger is a professor from ETH Zurich and also head of research in Anza. Yeah, without further ado, let's give this talk to Roger. Thank you.
Cool, yeah. Thanks for the intro. Yeah, glad to be here. So as we just heard, this is about Solana's new consensus protocol, Alpenglow. Uh, and maybe it will really be the new consensus protocol. There was a vote on it. Let me quickly show that. Yeah, but let me start with a bit of philosophy, okay? So, and usually I like to start with this quote from Thomas Watson, who was the chairman of IBM in the 1940s. And he said something back then, which maybe he didn't really say it, but people kind of put the words in his mouth. But people said back then there's a worldwide market for maybe 5 computers. And I like to fix that quote quickly. So if I move worldwide down here, if you kind of say there's a market for maybe 5 worldwide computers, then maybe you're very close to the truth that we'll see in the future. So currently we see many of these blockchain proposals, but we don't need that many eventually, like maybe some niche proposals will survive, but the question is are the proposals that actually survive? So uh, I think in order to be a worldwide computer in some sense, or to be a worldwide trust system, maybe would be a better word, you need maybe these 3 ingredients. You need performance, you need smart contracts, and you need decentralized. Performance is kind of clear. You want to have as many transactions as possible per second. Smart contracts should also be clear, sort of like you want to have, smart computations possible on your computer, and then you want to have it decentralized, so nobody should own it. And decentralized maybe because of this, for instance, this GameStop phenomenon at some point where you could not buy these shares anymore because the person who owned the market essentially was best friends with the person who didn't want to have you buy more shares anymore. That would be a typical example why we would want to have a truly decentralized system that nobody owns. Uh, I can also show it like this. So if you think about the developments in the last, maybe already 17 years now, people studied this consensus for a long time before that, actually, already in the 1980s and 70s and 90s. But then Bitcoin really was the one which introduced decentralization, right? That nobody really owned it anymore. And as a second step, Ethereum introduced smart contracts on top of essentially Bitcoin. Bitcoin had something like smart contracts initially, but then they kind of reduced their instructions over time because they felt they are not secure enough. And Ethereum actually took the risk there and added real smart contracts. And then now I work essentially for Solana, and Solana essentially added performance. Okay, so that's the third step. Now you can go full circle if you like. Let me add a fourth one here, just for the fun of it. So we can add Hyperliquid, and they are basically adding centralization back again. Okay, so kind of the thing that Bitcoin removed. Just having very few machines and basically owned by one company. Of course, that's faster, that's adding even more performance, but the question is, can you have decentralization, smart contracts, and really fast performance? Yeah, that's sort of like what we try to do with Alpenglow, and the point of my talk is just to now present Alpenglow to you uh, in the next maybe 30 or so minutes. First a bit, the motivation for it, and then maybe also, not just maybe, but also how it exactly works. And then I want to leave a bit of time at the end, more than usual, I would say, for such talks, to make sure that if you have questions, you can ask questions. But if you have questions throughout, you can also ask throughout, and I actually have the chat open on my phone next to me, and I'm happy to answer questions immediately if you have one. Okay? Does that sound okay? Good. So let me start. Yeah, so here is this vote I just talked about, this so-called SIMD 326. So whenever Solana tries to change something, it asks the stakeholders, which are the people who own the money, who own the Solana currency, whether they like the proposal or not. And this was the Alpenglow vote, basically. So you can see almost 99% of the people think this is a good idea. So this is probably going to come, right? There's not much, we're implementing it right now and we're testing it right now already. So eventually it will happen. This all started just last year when I was essentially hired. I'm still a professor at ETH, but mostly I'm now hired by Anza. This is the press statement they had back then. This is not just me, also two of my former PhD students were also hired at the same time, Kobe and Quentin, and the three of us basically developed this Alpenglow protocol. We are all from ETH Zurich, as you can see here, and I want to make a point that this is not Ethereum Zurich, right? This is actually university. Sometimes it's ranked very highly in computer science. So what we try to do is we try to follow the motto of Solana, and the motto is increase bandwidth, reduce latency. So we want to have high performance blockchain. And let me talk about these two things quickly. So bandwidth first. Actually, Solana already has super high bandwidth. So this means you can have many, many transactions per time unit, right? Many transactions per second. This is already true right now. And it has a lot of potential to have an even higher bandwidth even right now. So the system right now could handle probably not just thousands of transactions per second, but actually hundreds of thousands of transactions per second. And sometimes there are some tests on Solana, sometimes where very simple transactions actually already achieve that. Alpenglow can go a bit higher maybe, but not much higher. But conventional protocols are much lower. Usually in conventional protocols, you have something like a leader who has to do most of the work, right? So there's somebody who kind of has to gather all the transactions and send it to the others, either, maybe with some gossip protocol, but sort of like the leader is usually a bottleneck for this. And there are these DAG protocols, direct acyclic graph, something like SUI or Aptos, for instance. So they're already much, much better, but I don't think they can actually reach Solana's throughput. And I'll explain when I explain how we do it, why. And as I said before, Alpenglow is maybe a bit better, but not much better. Okay. So I already think that Solana, in some sense, is throughput optimal to some degree. And so this is already good, but maybe it's a bit better. And then latency is the other thing you want to do. So for latency, we have finality of Solana. This is how long it takes until a transaction is truly final once you send it to the blockchain. And this takes, maybe 12 seconds or something right now. This is pretty good. Most blockchains have a much, much slower finality time. For instance, Ethereum is much slower and Bitcoin is in the order of maybe an hour even or something like that. So that's even slower. So and maybe not even then it's final in some sense. So there's another way to express Solana's current finality time, and this is the so-called optimistic confirmation. So after 500 to 600 milliseconds after you send your transaction, you can be almost sure that the transaction will be final. You cannot be fully sure, but almost sure. So I'm comparing here a little bit apples and oranges on this slide. So this is a little bit different from what we really want. We really want something where you have guarantees that you cannot do better. So with Alpenglow, we bring this down. So people say 150 milliseconds sometimes they say 100 milliseconds. So that's sort of like what we try to achieve there. We want to have super fast finality. So 100 milliseconds is basically the time you need to send a message from somewhere in the world to somewhere else in the world, right? Like the worst kind of latency you can have in the world is like 100 milliseconds. So a bit above that probably, but not much. So this is really the apples to apples comparison here. So what we have now to what we had before, and that's really kind of 100 times better. And there's a competition, of course, and there are some chains which are better than, let's say, Ethereum or Bitcoin, which I mentioned before, and they can maybe get to 400 milliseconds roughly of latency or finality. That's also an apples to apples comparison, but it's a little bit a different apple, okay? Because this depends on many things, how you measure exactly, what's the sort of the distribution of the nodes in the world and stuff like that. So the real fair comparison is only Alpenglow with the current finality. Good, so this will be much better. Security, so we really want to make security much, much better right now. This mostly means that we want to have proofs for security, okay? So we want to have something where we can give formal proofs that this is a secure protocol given some assumptions. And in particular, we introduce something called the 20 plus 20 security, first time for Solana, I would say. This also goes back to research, of course, but what it means is that we can tolerate 20% arbitrarily malicious participation and 20% kind of, sort of crash failures and stuff like that, right? You kind of die for some time or you don't send messages for some time, stuff like that. So more, benevolent in some sense crashes. So this is new. So this gives you 40% total security, which is higher than even the 33% that you might have heard sometimes, which others try to achieve. We believe that this kind of Byzantine attacks will be very rare, okay? So Solana has something like $100 billion roughly, staked currency. And in order to attack the system with 20% Byzantine, security in some sense, you need $20 billion to attack the system, right? So this is a very high number, and actually as high as probably other chains. Maybe only Ethereum is slightly higher currently. And on top of that, we have, failure uh, tolerance for these crash failures, and these things actually happen quite often, right? So some nodes are misconfigured, or they turn off the node from some time, or they have a power problem or something like that, or a network problem. So this is actually more common case. That's why we said we really want to have a 40% security in total. I want to keep it simple. It's not as simple as it used to be. The first version of Alpenglow was very simple, and then we started to optimize it a little bit. So in some sense, it's a bit like this thing you might have seen. These are SpaceX's rockets. So the current version of Solana is kind of on the left, right? It's a highly complicated machine, and we try to simplify it as much as possible and make it better at the same time. Good. So that's sort of like what we try to do. Maybe a little bit of the history, how this worked. So we had this moment, like this Argentinian president at some point in front of a whiteboard. So he looked at the ministries of Argentina and figured out which ones he doesn't need anymore. And we had something very similar. We looked at kind of the main ingredients of the Solana protocol, and we wanted to know which ones do we not want to have anymore. Okay. And some of them you might have heard, maybe proof of history, you might have heard this. This is kind of the main idea of Solana right now, this Tower BFT consensus protocol they have right now, and so on. They use gossip. And basically, we stood in front of this whiteboard, and I would say these are really the main four ingredients apart from executing, and we kind of removed pretty much all of them. Turbine we liked, that's the data dissemination protocol, but even that we're going to improve with something called Rotor. And then we looked at the literature as well. We knew the consensus literature quite well, so we looked at recent papers, and these were basically our inspiration papers. So there's the simplex consensus protocol, for instance, which was an inspiration because it was very simple. And then there's Banyan, a paper that we wrote ourselves, which was the first one to do something like to have something like a fast path in a good way. I'm going to explain what this means, but these I would say were our main inspirations. So with these papers, we did something called Votor. So that's the voting part for Alpenglow. So we have Votor and Rotor. And these are the main two ingredients. I'm going to explain them quickly in the next maybe 15 minutes. If you have questions, please ask whenever you have a question. Let's start with Rotor. I have a bit of useless animation here. I apologize. But open the curtains for Rotor. So Rotor is the data dissemination protocol. How it works is like this. So in Solana, we have blocks. So transactions go into blocks. So that's standard in in many blockchains, of course, starting with Bitcoin already. And these blocks are disseminated over time, okay? So one block after the other, essentially. So let's look at such a block. The block is essentially the consensus entity. So there's many transactions inside a block, and we agree on what transactions are now valid, okay? That's what consensus will be about. Now let's look a bit more detail. So each block is cut into something called slices. So this is used for pipelining. This means we put a bunch of transactions into a slice and then we send them out immediately. And then we send out the next slice immediately and so on. So the transactions, once they have arrived at the leader who sends out these blocks, the slices go one after the other very quickly. And then each slice, as you can see here, I did it for the last slide here, is still partitioned into something called shreds. So that's just a minimal amount of data. So each shred you can think of like a UDP packet, something like 1500 bytes of data. Okay. So that's the minimum amount of data that we have, and a bunch of shreds together make a slice, and then a bunch of slices together make a block. Now, if you want to send out a slice, then we first cut it into shreds, and then actually we add a bunch of more shreds to it. Okay, so this is for fault tolerance. So this is erasure encoded here, all these shreds. So the idea is that if you see enough shreds of a slice, then you can recompute the slice very quickly. Okay, that's the basic idea. Actually, you need half the shreds that are sent out by the leader to reconstruct the slice. So let's see how this works. So we just look at the slice now. So the leader wants to send us such a slice. So there's a bunch of relay nodes. These are just randomly chosen nodes of the Solana system. So Solana is currently about something like 1200 or something machines or nodes. Actually, some of these nodes are many, many machines, but let's say 1200 people are in the Solana system right now, which take the role of the so-called validator. And the leader sends out, after making the shreds, the leader sends out shreds to these relays. On my picture here, there's 6 relays, but in reality, there's something like 64 relays which are chosen. So the leader has to send out 64 UDP packets, so that's not much data in some sense for a slice. And then the relays, when they get their shred, they do something very simple. They just send the shred out to everybody else. So you never have this little sunshine here. This means this relay has to send this shred out to the other 1200 or something nodes that are in the system, okay? So that everybody gets this shred. So that's the idea here. So this is sent to all nodes. You can send this really naively by just sending the same shred to, one after the other essentially, or you can make it a bit more smart by sending it out using some multicast, for instance, data dissemination scheme. That would also be possible. The relays, this is the main part of the work in Alpenglow, I would say. The relays will be getting money for doing this job, essentially. Okay, they get a little bit of money for whenever they send out some shreds. Good, that's basically data dissemination already. There's nothing more to it. It's very simple, I would say. I hope you agree with this when you see this. It's just leader sends out shreds, and then the shreds are just relayed by the relays. The voting part is also pretty simple, but compared to the Rotor, Votor is much more complicated, but let's quickly look at it. So here we have the blocks again. I made this picture a little bit more complicated because now here you see that you have always 4 blocks in a so-called window, and it's basically the leader window, we call it. So one leader sends out 4 blocks in a row and then gives the baton to the next leader so that the next leader can send out its 4 blocks. So that's how it actually works. Now we want those leaders to do a good job. And so far in Solana, this is done by proof of history, but we don't like proof of history, so this will be gone. So now we just use timeouts. So the idea is that, again, we have our 1200 nodes in the system. They expect these blocks, they expect the last slice of these blocks at some point in time. And essentially, they have a timeout. The timeout is just their local computation, just their local computer time, right? At some point, the timeout is started with the previous leader, essentially, or if that one was also not misbehaving, then with the previous leader. But but the timer is started at that point, and then basically everybody will just check, is block B4, for instance, in time? Was it only that much later than the previous block from the previous leader? And then they can basically vote yes or no. They can say, is the block correct? It should also be correct and in time. And if it's a yes, then they send out a yes. So they not only do this for the last block of a leader, but actually for every block of a leader. So in case the leader would be not doing their job, already doing funny things with the first block they have to send out, the nodes can vote this leader already down and skip to the next leader much quicker. So they just send yes or no. Let's assume it's a yes. And like before, they would just send this yes to everybody, okay? So that's the same operation as before. It's a very short message, but they send basically 1,200 messages around. So that's what every voter is doing. And again, they maybe get a little bit of money for that because that's actual work. Now, what happens with these votes? Let's look at the different sides. So I said everybody sends their votes to all the others. Now I'm taking the viewpoint of one of the others, basically. So they now collect these votes, right, up to 1,200 votes. Maybe some votes are missing, or some votes are up, yes, some votes are no. This is one case what could happen. So many votes are yes. Let's assume at least 80% of the votes are positive. What I mean by this is always the stake, right? So nodes basically have stake, they are smaller or bigger, and if 80% of the stake says yes, then it's already final, okay? This immediately finalizes the block in one single round of voting. So that's something very new, fresh, which has been introduced in Banyan. And we have this finalization certificate here. So I can make a certificate and by including these votes, basically, this is a so-called BLS certificate. It's also just one single message. It's only one UDP message. You don't need more than that. And you can send other people this finalization vote so that they also would believe at that point that this block was final. That already convinces them if they just get this so-called certificate. And you also send this out actually to everybody, just to be sure. And on the other extreme, we can have, maybe many, many downvotes. Maybe the block was really too late, and at some point the timeouts would fire at the nodes, and then they would send out a no vote. And if you get at least 60% no votes, then you can make a so-called skip certificate, same thing, but you would tell others, I want to skip this block. And if you have 60% of the votes in this skip BLS certificate, then everybody's convinced that this should be skipped. You send this out to everybody. So you can see these two things are quite far apart. 60% yes or no, or 80% yes. So of course there's many, many things in the middle. So it could look like this, for instance. So there's a bit, people don't agree on this. It could be a mixed solution. Now in any mixed solution, we would have a second round of voting, okay? So that's sort of what the protocol makes. In the simple solutions, either, hard on the right or hard on the left, then you immediately finalize the block. Either way, you either say it's good or it's bad. If it's mixed, then you need exactly one more round of voting. So the most common case for mixed might be something like 60% upvotes, not 80%, then you need another round. You can keep collecting votes. Maybe the many votes didn't come in, but if you reach 60%, then you would say, I'm trying to finalize this block now in the positive still. By just adding another round, you need another 60% of votes. This is essentially the whole voting protocol here. And as you can see, half of it I explained basically, but the other half is a bit tricky. And I'm not going to go through it line by line. Otherwise, we are here still in 1 hour or something. But that's basically, you can look it up in the white paper and you can, it's proof that it's correct and you can try to understand it. It's not very complicated, but it has like 60 lines of code or so. So this is the white paper I mentioned. There's a first version of it, and actually we have a second version of it that we released some months ago. Maybe at some point we make the next version, but just updating a little bit, making it a bit better if you can see other improvement possibilities. But let me show you a little bit what this means. So we have simulated this protocol, and this is such a simulation run essentially. So this is a so-called latency histogram. So at the x-axis at the bottom, you have the 1200 nodes I mentioned before. Now I didn't have space here for 1200 bars, so I made, a bunch of bars just every 10 nodes or so, or maybe a bar, or maybe every 20 nodes. I forgot what it was. So what it shows here is if the current leader was in, let's say, New York, how long would it take until you would receive these things? Okay, how long would it take until finalization? Now the green stuff here, this is the 200 millisecond bar, is just a network latency. Okay, so this is for other nodes in the Solana system. How far away are they from New York in terms of network latency? So you can see here on the left, these are nodes which are very close to New York, maybe in the US, maybe to the very left, they are also in New York, close by, or some other American nodes or Canadian nodes here, okay? And then the next plateau is actually some European nodes. Uh, Anywhere in Europe, you can see that they have all about the same distance from New York. It goes up slightly, but not so much. And then you can see there's a tail at the end, which is maybe nodes which are very far from New York, if we assume that the leader was in New York. You can see there's a ton of nodes in Europe, actually, so much more than you might have expected. But this is true not only for Solana, but also for instance, for Ethereum. A lot of stake is actually in Europe, and the reason for this is that just Europe is a bit more geographically centralized. This doesn't mean that people actually who own that stake are in Europe, but many of the machines are basically out of Europe. Now, I explained before Rotor. How long does it take until nodes see enough of these shreds so that they can reconstruct the slice, right? And you can see Rotor is a bit slower than just the absolute bare minimum of network latency, but not much more. Okay, it doesn't add much more to this lower bound. Then we can see the 60% voter vote. How long does it take until you get 60% of the stake having voted? That's the red overhead. And then you can see the finality, the blue stuff. That's the end of it, right? At that point, you know that this block is basically final. And that could be either 80% of the vote, as I explained before, or it could be 2 rounds of 60%, whatever is faster. Or it could be that you receive a finality certificate from somebody else. Any of these three things would convince you immediately that the block is final, okay? So that's the finality. You can see for New York, the median is slightly lower than 200 milliseconds, but actually New York is not so central for Solana. So we can go down. If you have, for instance, a European leader, then it's even less time. Yeah, so there's, you can find animations of this. So this is somebody has done a little animation of Rotor, how it would look like now for a European leader here. And yeah, just to notice, this little animation is actually slowed down so that you can see something, right? And in reality, it's 10 times faster than this. Okay. Uh, yeah, so here, like, real measurements show maybe 120 milliseconds end-to-end finality. Uh, Maybe I can't see the chat so well, but not sure whether something happened on chat or not, but I don't see anything. Good. Maybe towards the end of my presentation, a few more things, what we're working on, what are still problems that exist, okay? So the main open problems I would say right now that we are working on are maybe three things, but two are mentioned here. One is what we call migration here, or the switch. This is basically how to go from the current protocol to Alpenglow, okay? So we don't want to stop Solana and then do the migration. We want to keep it running, okay, without basically noticing that it changed the protocol. And this is very tricky, right? We have to change the engine. So this consensus protocol is basically at the heart of the whole blockchain. And we want to change the engine while running the machine, essentially, okay? So that's a bit difficult, but we're working on it and we have many good ideas how to do that. And another thing are working on is incentives. So how do we make sure that everybody does what they're supposed to do and, forwards the shreds, has relays fast and votes accordingly, correctly and whatnot, right? These things. And we have to work on these incentives. So these are the main two things. There are other things. For instance, we want to solve the so-called MEV problem, give some solution there to make sure that people cannot, front run transactions so easily, or people cannot sandwich transactions easily, and so on. So these are basically the things we work on. Maybe for incentives, I have one slide which says about, philosophically, what is the general problem here? So the general problem is validators, the people who run this system, they would say, I'm not Byzantine, I follow the rules, I'm not a malicious person. But kind of if you tell them that something could be a game, right? Maybe if they could make more money some way, if they deviated from the protocol, then they would immediately be interested. So it's very important that we don't have that, right? That changing the protocol, deviating from the protocol is not helpful. You don't make more money when you do that. So that's something we work on. We have a few incentives in place already. Maybe that's the last slide I'm showing here. This is kind of a whiteboard or a green board, I would say, with incentives. And now if we go to Alpenglow, we change these incentives a little bit, and maybe I explain this a little bit, just that you know a bit more deeper what we're trying to do. So currently, there could be something called forks in the system. That's also something Alpenglow can have. And you then have to vote on which branch of the fork where you would think that the real transactions are in there. Now, currently, if you vote wrongly, in some sense, if you vote on the branch which is eventually not taken, then you would be somewhat punished. You wouldn't get credits for that. And so many validators started to exactly show this behavior. They started to vote delays to delay votes essentially, to just see first what others are voting and then kind of decide with the majority in some sense to make sure that they get the money. But that would be bad, right? Because then everybody would vote later. So then Solana had to introduce something called timely vote credits. This is already all done. But timely vote credits would make sure that if you vote early, then you get more money than if you vote late, essentially. Now, with Alpenglow, we don't need any of this stuff. Essentially, with Alpenglow, what you see is what you vote. Okay, so if you see a block, and if it's in time, it's not before the timeout, you just vote yes. And if the block is, for instance, too late, then you vote no. You get the same reward no matter what you vote, right? So you don't need scheming. You don't need to think, would it be too late or too early for others as well? You just be honest about it. And that would help, right? If you get the same reward, then this is excellent. Currently in Solana, we have rewards for individual no votes. So the votes currently go on chain, actually. That's something which is special for Solana. Every vote has to go on chain, and we don't want to do that anymore. So now we just put these aggregates, these BLS aggregates on chain, right? And we kind of give the guy who voted some of the money and the guy who put the aggregate on chain some money. Maybe 50-50 split as it is conjectured here, or as it is proposed so far. And since individual votes go on chain, this is actually cost the validators have, right? So if you have to put your vote on chain, then you would get a reward for the vote, but you also have to pay for sort of the transaction which contains this vote right now. And the costs for that are actually quite high. There's something like one sol per day, so about $200. Unfortunately, the value went down badly the last few days, about $200 per day. So that's the cost to be a validator right now. And we don't need that anymore in Alpenglow because the votes don't go on chain anymore, only aggregates, and that's of course much, much less data. Not 1200 individual votes, but only one basically aggregated vote, which is just 1200 bits or something. So since we don't have that anymore, now we have aggregates which go on chain, we don't have this cost anymore. And this in some sense, so first when I said this, first people were excited about it because they felt, oh, now I'm going to save a lot of money because my transaction costs, I have no more transaction costs essentially for just voting. But that might be a problem, right? Because then we might have much, much more validators than we actually need. How many validators do you need, right? I don't think we need hundreds of thousands. I mean, Ethereum might think that, but we don't think that. So instead, we introduce something called a validator admission ticket. So you have to pay just an admission ticket to be validated, which is basically currently set to zero point 0.8 Sol per day. So a little bit lower than the transaction costs people had so far, but not much lower. So we want to kind of keep the economic incentive somewhat in play, at least at the beginning. We're already considering to change that, to not have this validator admission ticket anymore or this VAT anymore, but to have something else. But it's not so easy to do this right. Good. With this, I really want to, finish my short talk and basically give you some time to also discuss a little bit because I think that would be an interesting part for me as well. So just as a summary, I presented Rotor and Votor, the two main parts of the Alpenglow protocol. These are two pictures to remind you what they were. And then I showed you a little bit some simulation results, and by now we already have real results, and they kind of point towards maybe 120 milliseconds finality right now. And I told you a little bit about migration and incentives, which are the things that we still have to do. And with that, I'm done. Here's QR code if you like. You can go there and look at the original paper. And you can also just Google it, I guess. Uh, but if you are interested in reading the details, I would say the paper is decently written. So we wrote it in like a very modular way. So things you might just jump over. And the actual protocol is described on maybe one page, and then it's described in more detail later on. So that should be an easy and nice read. Good.
Yes. Yeah, thanks a lot. Thanks a lot for the wonderful talk. Yeah. Actually, I tried to finish the reading the white paper, but it's too long.
It
Yeah,
is.
but I think it's very very well organized. You put protocol,
Yeah.
intuition, those things, analysis.
Yeah.
So it's very
No, it's very,
helpful.
very long. I agree. But let's say
Yeah.
that, after page 20 or so, there's only, for me personally, I would think if you read from page 10 to 15, then you have
Yeah,
read the
yeah.
most of
I
the.
finished about 20 pages. Yeah.
Yeah, yeah, yeah.
Yeah, let's
Sure.
see other questions. Actually, I know one person from Beijing, from China. It's early
Yeah.
morning. I wonder if we want to open mic, ask question by yourself, or I can. Otherwise, I can read for you. I
Sure.
put
No, I mean, I see it in the chat, I think. You mean forwarded Q1, for instance?
yeah yeah he put questions there.
Yeah, yeah,
Basically, yeah, let me read. So,
yeah,
since we are recording, so the people can know what the question is. The first question is, under the Alpenglow consensus, what are good solutions for achieving fast submission and execution of transactions? The
yeah,
faster, the better serving trades. Yeah, I think this is from the business side to do trading
yeah.
on what kind of solution may be good, yeah, for those traders.
Yeah, for the traders, I mean, the way it's written right now, right? If you want your trade to be executed fast, then you should send it to the leader, the fastest way you can, essentially. I mean, there are different ways how to do that. If you're a big trader, maybe even directly is a possibility, but there are various ways how to basically ramp up send your trade to the leader. And then, as I explained, in some sense, if you're at the end of the block, right, sending out the rest of the block, and then doing the execution, doing the voting on the block and whatnot, that costs maybe between, well, such let's say around 120 milliseconds. So 120 milliseconds, your transaction would already be finalized, okay? And you would have a proof that it's already finalized. So that's in some sense the thing you can do. If you are at the beginning of the block, it will be a bit slower still because the whole block first has to be sent out, and that takes a bit more time. But we're working on this as well. So maybe we make block time a bit shorter. Now it's 400 milliseconds. We can surely, half it or something, and then it's maybe even faster. So we're trying to push there as much as possible. So we want to be the fastest blockchain, the fastest worldwide blockchain for sure. And if anybody else is ever faster, we're gonna improve it again. Yeah.
Yeah, just
So that's
yeah. It's just a
Would feel good.
follow-up, maybe.
Yeah.
I have not checked the literature yet. I wonder if there may be some AI technique to help, traders to find what's a good way to, say, maybe pay for transaction fee or some other technique.
Yeah.
Maybe AI can help to f figure out some way. I don't know. I don't know yet. I have not checked the literature. No.
Sure. Yeah.
Okay. But anyway, yeah.
Yeah.
The second question is, how many consensus nodes, validators does Alpenglow consensus support in theory?
Yeah.
After the upgrade, how many will be limited in practical applications?
No, that's a good question. Since I talked about it as well, it works well with my talk. So I said in the talk, currently we have about 1,200 validators, 1,200 nodes in Alpenglow. In theory, Alpenglow supports as many as you want, okay? There's no upper limit really. However, in practice, we're gonna limit it. And the reason for it is that if you have more and more nodes, right, some of the jobs that I explained, always these little sunshines I had, it always meant that you have to send to everybody essentially. And of course, if you have 100,000 nodes, that would be much more work than sending just to 1,000 nodes, okay? So it would be 100 times more work essentially, right? So we don't really want that, right? That would slow down the protocol to some degree, even at some point. Uh, Also, we kind of like this idea that everything we have fits into a single message, into a single UDP message. You never have to send multiple messages to send something to somebody else. All the shreds and all the votes and everything, all the transactions actually, they all fit in a single UDP message. This makes the design much nicer in some sense. And because of this, we're gonna limit. Because of this, maybe we would have to limit something like 4,000 or something nodes at most. And actually, in practice, at the beginning at least, we're going to limit even more. We're going to limit to at most 2,000 nodes. Just, to not have a huge disruption. We don't want to kind of deliver Alpenglow. And then on the first day, like when we change to Alpenglow, all of a sudden we have, 10,000 nodes instead of 1,000 now. That would make it hard for us to understand what's going on, right? So it's better for us to, if we kind of have, a transition to Alpenglow, which is sort of like similar to now. So that's why we limited to 2,000 at the beginning.
Yeah, okay.
Yeah.
Uh, yeah, the third question from Beijing is, will the Solana mainnet consensus be upgraded to the OpenGrow algorithm in 2025? I guess it's 2026, right?
No, it could be. It's still 2025 now. So
Oh,
with implementation, I would say all the normal path implementation we have already done, right? So this all runs already. There's several test nets where Alpenglow is running already. So one, for instance, has about only 50 nodes in right now, but they're from a third is from America, a third is from Europe, and a third is from Asia. And so this is the 120 millisecond testnet we have right now. So that works already. But the thing is, right, so I would say on testnet, we probably have the whole Alpenglow implemented in 2025, okay, and running in 2025. But to go to mainnet, we really want to test it well, right? You don't want to do something, there could be some coding mistake somewhere, and you don't want to go live with something which is not, I want to be sure essentially that I can sleep well that night. So maybe that is beginning of 2026 when we actually will run Alpenglow on Solana.
yeah, yeah, great, thank you. Yeah, this basically finished the question from Beijing.
Yeah.
Other questions, from the audience? Uh,
Yeah, there's one by Wade. Maybe I can
oh yeah,
quickly
that's the
go
same
into
same
that.
one, the
Yeah.
same one. Yeah, actually just from him, from Wade. Yeah, that's the first
Ah, that's
question.
that's yeah, that's very similar, right? So yeah,
Yeah, that's the first question. Yeah, yeah.
yeah,
So,
okay.
are there more questions from the audience, Samir or other people? Yeah, let me see. I prepared two.
Yeah.
Let me put it here. But
Oh,
I prefer to wait other people before I ask those questions. Let's say three, two, one. If no, let me ask. Yeah. So let me read. So in for traditional database, has the ACID, the atomicity, consistency, isolation, durability properties. And blockchain is a distributed ledger, and so it's actually a database.
Yeah,
But consensus protocols like POW, POS, and Alpenglow, I think they basically follow the randomized algorithms. So it has statistical guarantee. Although you can prove something, right? It's statistical guarantee.
yeah,
It's not like in the traditional database. Traditional database they are basically following the logic, so it's fully guaranteed if it's
yeah,
guaranteed.
yeah,
So there may be some gap, right? So when we want to apply like those blockchain, including Solana, including OpenGlow, to
yeah.
because like payments, we hope to have perfect guarantee maybe, but how about those randomized algorithms? Yeah, what's your opinion? Is my understanding correct, right? So if
Yes,
so, what may be the problem? Other problems or not?
yes. So I mean, I would say my fast answer, okay, is that for sure it has this acid stuff as well, okay? Okay, let me try to explain, okay? So first of all, we have transactions, right? So transactions, this is like databases exactly, right? It's coming from there. They have atomicity. So you either execute a transaction or you don't, right? If the transaction is correct and in a block and the block is finalized, then we execute, right? And the same thing for consistency, isolation, durability. So there it actually helps that the transactions are in some sense they're sequential, or at least right now. So if transactions can be executed in parallel, they can also be executed in parallel. And Solana does that. But then they will just touch different parts of the memory essentially. So only simple parallelism somehow. So they are isolated. They logically they are run one after the other. They are consistent. They would take the state from the last transaction. They are durable. Once you have, finalization, then you know that this is for real, right? Like if you see finalization, then other nodes will also see it. I would argue that in some sense, right? So in some sense, this is even better than a database, right? Because in a database, at least classically, right? You have one single machine, and that's the database, right? If this machine has a problem, right, it goes down, or there's an attack on the machine or something like that, then you immediately don't have these things anymore, right? For instance, durability, you don't have anymore, right? So, uh, so in a distributed system, in a blockchain system, this should actually be much, much better because we can rely on, thousands of nodes essentially, and if only, some of them survive, then we know that this survives. Like, for security reason, only one machine needs to survive even, right? And even that would be enough to make sure that we still know who owns what, right? So this is really an acid version of acid in some sense. Now you can say it's randomized. So the algorithm itself actually is not very randomized. We don't really use much randomization. We have a bit of randomization here and there, but this is just to make the protocol more secure. For instance, by choosing the relays, this is somewhat randomized, right? If you want to do the data dissemination, then you don't choose them deterministically, because if you always chose the wrong one, so to speak, then it would not forward the data or something like that. But uh, but it's really, I would go on stage and I would say it's stronger than a traditional database. Of course, you could have, uh, very bad network situations. For instance, the internet is basically down, right? All the messages take much longer than they should, or maybe they don't arrive at all. But I would say this is then you have the same problem in a traditional database, right? If you want to put a transaction in from Toronto and the server is somewhere, let's say in Beijing, and the internet is down, then you don't really have a good proof there. But we can prove that if in the so-called partial synchrony model, and this is that we are secure. Now, partial synchrony means that basically the internet can even be bad and nothing bad happens. At that point, you just don't have much progress. Okay, if you have a very bad internet, then the progress is very slow or maybe not even existent. But if the internet comes back and is good again, then we can guarantee that we have, fast finality, as sketched before. So this is basically what we can prove. And so I would say you can trust this a lot, right? So I would say, for the future, if we have, or already now, let's say for a protocol which has aged like Bitcoin, they have not seen, failure anymore in a long time, then then I would trust this system much, much more with my transactions than any other system, right? Because most other systems are not decentralized, they are centralized. So you have to trust, a single machine, or you have to trust a single operator, or a single company, or a single government, or something like that, right? And that's in some sense much, much worse than having this blockchain system, which is a bad name, but it really is a decentralized, system where you don't have to trust anybody individually anymore. Yeah, sorry for the long answer.
Yeah, yeah, I think that's great. Maybe a short takeaway is blockchains do not yeah, people using blockchains do not need to worry about those ASIC properties, and blockchain has better properties than the
I would
traditional
say
database.
it's
Yeah,
almost better, right? In some sense, it's almost better. I mean, we have different properties, usually what we want, right? We want fast finality, we want high throughput and whatnot. And then we have these, magic percentage numbers, which are in the question too, but I'll let you ask you first. And that's sort of our guarantees, right? So ACID was in some sense replaced by these security numbers that we have, that we say only that many machines have to be alive in order to
yeah.
make progress, and only the internet only has to be that good and stuff like that. Yeah.
Yeah. Okay. Yeah. Thank you. Yeah. For the second question, there are many numbers in the opt-in flow,
Mhm.
open flow protocols. For example, 80%, 60%, 20 plus 20. Those numbers. I think these
Yeah.
are basically hyperparameters. Yeah. My background in AI is with learning, so when I read the paper, I think in this way. And in recent years, there are people trying to optimize and automate, algorithms.
Yeah.
For example,
Yeah.
even protocol design. So I'm wondering whether there may be AI techniques, for example, search, reinforcement learning, may be helpful to decide design those protocols to decide those parameters. So
Yeah.
yeah, what's your other, or even are you working on this, or some plan to do
Uh,
similar things? So
I have been working on, in other domains, I have been working on improving, let's say some parameters using AI. I know a little bit about this, but here it's not needed. So the numbers I said, they are indeed optimal. Okay. So if you want to have a one round finalization, you cannot have, like what we want essentially, you want a fast finalization, then you cannot have more than 20% Byzantine nodes. We can prove that.
okay,
And also the 60%, so the 80% to 60%, we can prove that those numbers are all optimal. They cannot be improved anymore. If you would change these numbers only slightly, then we can always give you a tax. And this is not only, this is even more than what I just claimed. So this is even, these numbers are even true for any protocol, right? So if you want any consensus protocol, you can, in one round finality, you cannot be better than 20% Byzantine malicious attackers. So this has
okay,
been proved by us and by others before, and we achieve these highest possible numbers. Now, if you want a multi-round protocol, if you like, if you want to have multiple votes to get consensus, then you can improve to 20%. And this 33% is a famous, yeah, uh, is a famous other bound that exists. And protocols like Ethereum, they try to achieve the 33%. Yeah.
okay. Yeah, yeah. Thank you. So basically, I think it's something like the one third in the classical Byzantine
Yeah.
protocol, right?
Yeah.
It's
Yeah. That
it's
would be.
basically
Yeah.
from theory. Okay, yeah. Yeah, but maybe, yeah, what I want to say is, in the protocol design, there are many hyperparameters. Some of them may be, searched by AI, but I don't know.
Uh, yeah, but like for these things, I would say, I like AI more than the next guy, I would say. But for
Okay.
these things, you can also trust, like three researchers which thought about it for a long time. And actually also others, people have started looking at proof systems to show whether they can
Oh,
more formally even prove that our protocol is correct. So these things exist, and we have a few things where maybe AI could help, but I would say regarding algorithms, AI is maybe it's quite okay doing code of things people have done before, but it's not so good developing algorithms yet. So
yeah,
there's,
yeah.
there's still a few
Oh,
more years.
yeah, yeah. Just now you mentioned the proof. So I just wonder whether Alpenglow has been formally verified or not yet.
Yeah.
Oh,
Yeah, I
it's
know some
already.
people. Yeah, there's like two teams I know in the world which have looked at this, and they have implemented Alpenglow in their formal proof system. And yeah, they sometimes on Twitter you see them that they show their results or something, but nobody has found a mistake so far. I
Okay.
mean, if we have mistakes, I would expect that the code, of course, is a different story, right? Because the actual real code has maybe 10,000 lines or maybe even more, right? And so that will be the if there's
Yeah.
a mistake, then it's there.
Yeah. Phone proof, that would be very helpful, especially for, software like the OpenGlow, this level.
Yeah,
That's
yeah,
so critical for blockchain.
yeah.
I wonder if there are questions.
Yeah, there was a question about Twitter. So my Twitter handle is on the bottom right of this page here.
Yeah,
And the Twitter handle of my co-authors is also on this page.
yeah. Maybe, yeah. If there are no others, let me ask two quick questions. One is,
Yeah.
how about you? The results are there just by one run? It on real system is multi-run or something. You saw some results for the latency.
The result for the latency?
Yeah, is that for just for one run for a real system or for simulation
Yeah.
or something?
Yeah, this is like the one I showed is just really just simulation where we look at the distribution of the geographic distribution of the stake in Solana, and then we simulate this basically. So that's sort of like what we did there. And then the 120 milliseconds, this one tweet that I shared on one of my slides. So this is from one of the early, actual implementations in a test net. So there's more and more. I'm more and more convinced that the numbers I gave out in the first talk should be about correct. Yeah.
Okay. Maybe let me ask the last question is, on your second to last slides, you put lots of the incentive, those things. Are there, you know, ideally we have incentive compatibility. So are these already proved in that way or, uh,
Yeah, good question. So for incentives, we are still working on this, I would say. So this will be more difficult. We haven't proved yet that if you deviate from the protocol, we haven't formally proved it that you cannot make more money. I have a strong belief in that, but there's still no formal proof for that. Yeah, we still need that.
yeah, but I think that's a very good starting point. So just like,
Yeah,
just like Bitcoin, right? Bitcoin, when they put the white paper, there are lots of things to be done. So maybe OpenGlow is at that point and a good starting point, so people can keep working on that. There will be
yeah,
some,
yeah,
yeah, many work to make it better and better, I guess,
yeah.
in that
Sure.
sense.
Yeah, I
Yeah,
agree. Yeah.
yeah,
Oh, cool. Yeah. No.
yeah.
Yeah. So
I
thanks for
think,
inviting me. And if you have questions, you can send me a tweet or something. That's fine. Yeah.
yeah. Thanks a lot for the wonderful talk.
Okay.
It's very
Thank
nice.
you. Yeah, it
Thank
was my
you. Thanks a
pleasure. Yeah.
lot. Yeah,
Thank you.
yeah.
Bye bye.
Bye. Thank you. Thanks a lot.
Thanks. Yeah.
Okay, let me finish this.